We're going to define thermal conductivity, and we will talk about transport of energy in the upcoming videos. So we can show the definition of thermal conductivity by considering a substance that is in thermal contact between two thermal reservoirs or heat reservoirs. One is cold at temperature T1 and one is hot at temperature T2. So the substance lies in between Z is equal to 0 and Z is equal to L. And in this scenario, basically, we can talk about the heat flow reference direction as the positive Z direction. So for T2 greater than T1, so we have a substance in thermal contact with a heat reservoir at temperature T1 and another heat reservoir at temperature T2. And basically we're saying that T2 is greater than T1. So heat will flow from top to bottom, from hot to the cold side. So if we define the heat flux QZ, this is basically heat flow per area per unit time. So considering Z is equal to a constant plane between Z equals 0 and Z equals L, we have the heat flowing per area per unit time. And as you can see, since the hot side is at the top, this is going to be negative. So it's not positive. So with this convention, it's going to be negative. So we have this boundary condition that the temperature of the substance is a function of Z, such that at Z is equal to 0, the temperature is T1, and at Z is equal to L, the temperature is T2. Now, the heat flux QZ basically depends on the gradient of temperature, and as you can see, it's while the temperature is increasing from bottom to top, the heat is flowing from top to bottom, so we need to introduce a minus sign. So there is the proportionality constant Kappa multiplied by the temperature gradient del T del Z for one-dimensional heat flow. So this is basically a first approximation, and this linear relationship between the temperature gradient and the heat flux is valid if the temperature gradient is not too large. So this approximation gets better and better when the temperature gradient becomes smaller. So this coefficient, the constant proportionality constant kappa, is called coefficient of thermal conductivity, And if we do a dimensional analysis on this equation that defines the coefficient of thermal conductivity, we have the heat flow. So heat is a type of energy, so it's measured in joules or calories, and joules per area meter square per unit time second. This is the dimension of kappa, so unit of kappa, multiplied with the temperature change, delta T in Kelvin, divided by meters. So you can see that this meter will decrease, and joules per second is basically watts. So the unit of kappa is watts per meter Kelvin. And kappa is also always a positive quantity, and as you can see, when you have the temperature gradient positive, del T, del Z is positive, the heat flux has to be negative, because the heat always flows from hot object to the cold object, which is basically due to the second law of thermodynamics. So if you look at the entropy change in the total system, you find that the total entropy change is going to be the entropy of the isolated system, total system, will be maximized only if you have the heat flow from hot side to the cold side. So basically, in agreement with the second law of thermodynamics, we have the heat flux negative for a positive temperature gradient, and therefore the coefficient of thermal conductivity is always positive. So we have found the unit of thermal conductivity, and we have found that it always should be positive, because that's the way it was introduced in this equation that relates the heat flux to the temperature gradient. So when we have a substance in thermal contact with a heat reservoir at a cold temperature T1 and another heat reservoir at which is hot at a high temperature T2, when T2 is greater than T1, heat always flows from top to bottom. The heat flux is defined as heat flow per area per time, and it is proportional to the temperature gradient with a proportionality constant minus kappa. And the minus sign comes from the fact that the heat flows always from hot to cold objects, so the direction of the heat flux is opposite to the direction of increasing temperature. And this relationship, this linear relationship between temperature gradient and heat flux, is correct to a first approximation if the gradient is not too large. And kappa is called the coefficient of thermal conductivity. It is measured in units of watts per meter Kelvin in SI units, and it's always a positive quantity.